Today we are going to explore how to design parallel programs for multi-core systems using simple C++ thread-based examples. Before jumping into patterns and theory, let's start with a basic idea, which is the difference between sequential and parallel execution. Let me create a simple program to compute a sum sequentially. First, I'm going to be including libraries. I need a thread and a container vector. Main function, and inside main function I'm going to be having vector container name array of size 1,000,000 items, all set to 1, and I would like to have long sum equals to 0, and I'm going to be having a function. The written type long and partial sum. Vector parameter, and we have some variable size 0 for int I equals to 0, I less than I plus plus, sum plus equals to ARI, and we finally return the computed sum. So this is the function which will calculate the summation, and we'd like to call that function, store result in this variable, and we display so we have because we have the same variable name, so name of the function and variable, that's causing problem. So we want to change this name, maybe compute partial sum. It's going to be ultimately going to be partial sum, so I'm just using that name now. Use partial sum. Vector undefined partial sum here. So now this code should be working. I'm going to be switched to the terminal and see whether we have any issues with this. So we have this in the code, so I'm going to be compiling this C++. Output file. So this is just a warning, we can ignore it, main.exe. So now total summation is 1,000,000 itself. So we had a vector of 1,000,000 elements with is set to 1, so naturally total summation would be 1,000,000 here. Now what I'm going to be demonstrating is to call this function 2 times and get 2 sums called as partial sum. So half of the elements will be added in one invocation, and the rest half will be added in the second invocation. So for that we need to have two variables, call it sum1 and sum2 equals to 0, and then we're going to be here we want to just keep track of the elements we want to sum. So receive int begin int end, and we want to start from end, right? Now from begin to end, then we call this, we pass 0. In the first case we pass 0 to ARR size divided by 2, and we store that in variable sum1, and we call sum2 equals to partial sum ARR dot size divided by 2. So this will compute two sum values, and when we display, we want to display summation of two values. So this is the invocation of the function in two stages, where each stage actually computes the partial sum, but in sequence, one after another. So this sum1 is computed first, and then after that sum2 is computed. So they cannot they can be executed at the same time. So to the terminal, we compile again, execute, we still get the same thing, same value. So up to this point this program executes it sequentially, one operation at a time, one partial sum operation at a time. It's in the single thread. You can also, if you call this entire function to compute the total summation at the same time using one thread, that is also one sequential operation. Now if we want to see this being executed in two independent threads for parallel execution, we want to execute this function invocation in one thread and this invocation in another thread, right? So we can create something like this thread called T1 and pass the function to it, partial sum just comment this out for a moment. Let's put this here. So here the issue is we need to capture the return type. So the thread, if you invoke the thread, if you create a thread to call this function like this, there's no way you can capture. So what we can do is maybe we can have a lambda expression. So inside lambda expression we can call that function sum1 equals to sum ARR 0 size by 2. So and then so we can do like this, but to make this happen, this is sum1 and this array ARR, these are the things that are defined in this scope, so which are not directly accessible in the lambda expression. You need to capture these variables. So we capture this sum1 by reference and also by reference. So now they are accessible, and then computed value of sum would be stored in this variable. Now similarly we want to have another thread, call it T2, and in this case we are capturing sum2 and 2 here, but the range we want to compute is we start from this array size by 2 and size. So and then finally you need to join the threads back. So t1 dot join, t2 dot join. So now these are actually executing in parallel together. It's not that this t2 will be running the function after the completion of after t1 finishes running the function. They actually execute in concurrence, and then this statement do synchronization. They actually wait for the two threads to complete and join the back to the main thread, and then the result is used afterwards. So let us see this in the terminal. Compilation, execution, we still have the same result, right? So but at this time it was computed through concurrent execution by using multi-threading. Now both halves again, to repeat, first half and second half of this array, both halves are actually processed in parallel. So the key idea is simple. Instead of one execution flow, we divide work into multiple flows running simultaneously. This is the foundation of everything we are going to discuss today. Now the important question is, how do we design such parallel programs systematically? For that we use a simple framework called PCAM. PCAM stands for partitioning, communication, agglomeration, and mapping. These are the steps we follow to properly design parallel algorithms. Let's understand it using simple example, matrix processing. First we partition the data, for example, a split matrix into rows. Then we identify communication. Do threads need to share results? Then we agglomerate, group small tasks into larger chunks. Finally, we map, assign tasks to threads or cores. Each stage visually transforms the same matrix processing problem. So, PCAM is not code. It is a thinking process before coding. A simple pseudocode like this is a typical result of applying a PCAM model where we divide the data, process it in parallel, and then combine the results. Let's start with the simplest pattern, task parallelism. Here, tasks are independent and can run in parallel. Now let's implement this idea in code. Here I am going to be demonstrating two versions of task parallelism based on behavior. The first is going to be data driven, where the behavior of the task is determined by the data. And another is code driven, by code or logic. So we are going to have first let me create a task function which receives a string activity, and we display that activity. Now in the main function I create a thread tags, and then if I call this kind of tags, then I need to pass the parameter. So activity would be, I want to the tags I want to have, or I want this thread to perform the task of downloading file. So it will display this text. That means that task is performing this kind of emulation of downloading file just by displaying the text. And the next activity we want to do is play music. So then we need to synchronize t1.join and t2.join. So this is two tasks being set in execution by through two threads. One is to download file, another is to play music. And now at this point, I mean, we have one task, but we're talking about the task splitting. So splitting happens at this point. When the threads are created, and the tasks are split manually by assigning different function arguments to different threads, making each thread responsible for an independent activity. And this is we can also call this as a parameterized task execution. We have a same function, and we have a different behavior. Controlled by the argument. So let us see this in the execution, the terminal. So it has completed, so displayed the expected text. So now we want to be more explicit when defining the tags. Another way of doing it is create two different files. Instead of having the tags function passing the arguments to the parameter, you have download file tags, and we're going to have play music tags. Make it smaller. So now instead of having the threading like this, we would like to do something like that. I mean, we want to just create thread T3 and just set the tags into execution. So in this case, in this lower case, it is explicit function based decomposition. We have different functions, and each function defines a distinct task. So these are the two type of tasks splitting. In both cases, the tasks are independent. In the first version, we use one function with different inputs. In the second version, we use separate functions for each task. Since the tasks are independent, no communication between threads is required in this example. This pattern is used when tasks are independent, like services running in a system. Now let's move to a more powerful pattern, divide and conquer. This is where we recursively split a problem into smaller parts. Let's go into coding again. I am going to be demonstrating merge sort approach through coding, which is based on implementing or using divide and conquer method, or the method we are currently talking about. So we have the library IOStream, thread, and vector are going to be used, and in the main function, I'm going to be having a small array just to demonstrate the sorting in the vector. Initialize it to 9, 5, 1, 8, 3, 7, 2, and 6. And we want to have a function, for example, pass array to it, and we also want to send the index, the range of index where we want to do sorting. And size, first element, last element, and then once it is done, we will be printing for int x, range based for loop x. So this is the main function, and we want to implement merge sorting here. So the function is void sort, and it should receive vector in type, and it should also receive start and right. Let me call it, usually they prefer to call use this term, left and right, and the purpose is to sort this array, or if we are in the recursive call, then this can be a sub array as well. So array or sub array, this array with element starting with the index left and left right -1, using divide and conquer strategy. So what we want to do is we will be having the recursive call, and until a situation where we have this right minus left is less than or equal to 1. Either they are equal or right is becomes smaller than left. So if right minus left is less than or equal to 1, then we have some exit strategy, because we cannot infinitely continue recursing calling the function from inside. That will be lead to the runtime error. So infinite function invocation. In this case, we return stop. This is what determines the exit strategy, or sometimes it's also called as the base case. Right, it checks whether the array is already short. Right, so when array is already short, and the control will get into this step. Now if not shorted, Then we want to determine the mid index between left and right. So int mid index is equal to left plus right divided by 2. This is used to divide the array into left half index is starting from left to mid minus 1, and starting and right half with index starting from mid to right minus 1. Now we want to run this function in parallel in 2 threads. So because the return type is void, so we can directly put this in a thread. We don't need to use the lambda expression like we did in the previous exercise. T1 and call the function and pass the arguments. So if you, I mean, in this case we want this change that is made by the call invocation to reflect in this scope. So we want to pass a reference of ARR. You need to explicitly pass as a reference when you are passing into this thread, when you're creating thread, and then we're passing left and mid in the first case, and this will sort left half, then thread T2, and then you pass mid to right. So it will sort but both run simultaneously at the same time. And again, this will pass array by reference, and it will avoid copying the array. Right, then once it is done, the task is completed, then we do joining. Then after that, you will be having this first half, second half, so you need to actually merge, because in each recursive invocation you may have this left sub array, right sub array being, the elements from left to mid, left sub array, and elements from mid to right sub array are individually sorted, and but when you combine them, you need to merge properly so that entire array looks sorted. Therefore we want to use some merge algorithm, and for that we want to use a function called you can create your own function. This is the function that is available in STL library called algorithm, and you pass the first element plus left, and this is the range you want to merge with another range. So it will merge in place. That means it will not use extra array. It will just rewrite the array by merging the left content and right content into it. So this is the function merge sort, and we have the invocation of that function, and this will display. So let us see whether this code works or not first. We want to make sure everything is okay so far. So we are compiling. So looks like the output is sorted 1 2 3 5 6 7 8 9. So it is sorted, and it is sorted through the merge sort, divide and conquer approach, specifically merge sorting method. In this case, each half is sorted. Just a point to note here is that through multi-threading they are sorted independently. It is not like that left half is sorted first, and then after that right half is sorted. They are sorted independently, and then we merge the results here. And this pattern is very important because it naturally exposes a parallelism in recursive algorithms. So recursive algorithm that this is calling from inside it is inherently parallel algorithm. So this actually exposes that. Now let's look at a data driven parallelism. Instead of splitting tasks, we split data. Each processor performs the same operation but on different portions of the data. Consider a two-dimensional image. To process the image in parallel, we divide it into chunks and distribute those chunks across processors. In one-dimensional decomposition, the image is split in only one direction. For example, each processor may receive a group of rows. This approach is simple and commonly used. In two-dimensional decomposition, the image is split in both directions. Each processor receives a small rectangular block. This often improves load balancing and reduces communication overhead in large-scale systems. One-dimensional decomposition divides data in a single direction. Two-dimensional decomposition divides data into smaller blocks. Two-dimensional approaches are often more scalable for large scientific and image processing applications. Let me explain this through coding. Here I am demonstrating how geometric decomposition can be carried out for two-dimensional like array, 2D array. So we have the necessary library here, and we want to create a 2D array of, let's say, integer type. Call it a grid, 2D grid, and we want to have a size defined. Size equals to 8 by 8. So size, this is will define two-dimensional array, and we are going to be using this to emulate kind of image and to use it to demonstrate the geometric decomposition. So for that, let me create a tags first. So the tags will be, let's call, first we want to divide row by row, right? So we divide we want to create a tags function that processes the row. So call it process row and start so one row will be for int j equals 0, j less than size, j plus plus, and if you want to, for example, add 1 to all the row elements, right? So this is the loop that will process one particular row, but we need to also give specify the row identifier. So just to make things simple, we can have this as a task that does processing, but by row, one by one. So maybe we can have something like this, int I equals to start I less than int I plus plus. We want this this logic to process the rows beginning from start to end. So now to process this row in parallel, we can use a thread like we did before. Create a thread T1, and since we want to only pass the integer value, so we don't need to create a variable, so we can directly pass it. So T1 the tags, and then we want to process in one thread. We want to pass from starting from 0 to, we can have size by 2 half, and we can have another thread to process the next half. So these two threads will run in parallel in concurrency, and we can display some message which indicates that processing has completed. Create array processed, and before that we want to join the threads back. Right, I think this is actually geometric decomposition. We are decomposing, dividing, let's say, a matrix. It could be image or something like that. So we are dividing this this to be computed separately than from computation or processing of this rows. And the first thread is actually processing first 4 rows, and the second thread is processing the second rows. Second, group of the rows, second half of the rows. Let's see. We want to make sure that we don't have any issue with this code. So going back to the terminal, and so it is processed, right? We don't have any issue with that. So but it has been processed using 2 threads. So this is processing the rows. Now it's also, a practice. It's also a useful practice to process in block, not in rows. For example, if I have something like this, A, B, C, D, E, F, something like this, and G, H, I, J, K, L. These are the, if you assume that these are the data values, you can select this blocks, right? For example, if I want to process this entire image, then I want to select one block in the left side, do processing that, do that, and another block, another block, another block, and use individual threads to process those blocks in parallel. So that is the idea. So for that we need to design this tags a bit differently. So call it process block, and in this case we want to give specify start and end for rows as well as a start and end for the columns. So int row start, int row end, int start, int column end. Now the loop is pretty much similar. I can just copy this for loop and paste here, but we need to use for the column we want to use column start to column end, and for the row we are using row end. So it will only pick that particular block of element in that combination of row and columns and do processing to those elements. And for this, maybe I don't want to execute this functions in this case. So meaning when I'm using this, I don't want this code to be executed. For that, let me use preprocessor directive just to block that code. Block division, and if I want to do block division, so for example, if maybe ignore this for a moment, just here we can use here. So if not defined, we want to continue, we want to execute this else. So we want to put the code that will actually do block division in this place. We want to split this entire this space, this grid, into 4 different blocks, and 4 blocks, left right, top left, top right, bottom left, bottom right, and we want 4 different threads to process those blocks. So for this we want to have split into 4 2 times 2 blocks. T1, and the rows I want to work with is 0 to 4 in the first case, and then column 0 to 4, and T2, let me check the name, PROCSS block process, and then it's going to be 4 to 8 row, and the column is going to be 0 to 4 rows, same rows, and column is 4 to 8. And then we have another thread, T3, and now it's this I mean here we're going to have 4 to 8 for the rows and 0 to 4 for the columns. T4, it's going to be 4 to 8 and then 4 to 8. So this will process will process top left block in the grid. This will process top top right block, and this will process bottom left block, and this will be right block. Then after that we need to join the threads back. T2 dot join, and we want to display the message grid array processed. This is a block splitting version, or you can also call the 2D decomposition using So let us see this in action. Since we have this defined, this symbol, and then we this code should not be used by the compiler, and compiler will have after compilation pre-processing main will have this code only there, so should be okay. So in the terminal, so it is processed. We don't have any problem with this, right? Now here each thread processes a different portion of the grid, either in this case or in this case, and this is widely used. This approach is widely used in image processing, in simulations, and GPU computing. Now let's move to pipeline decomposition. It is like an assembly line. Pipeline decomposition is another form of parallelism where a task is divided into sequential stages. Instead of splitting data or tasks randomly, we organize computation as a pipeline of steps. Each stage performs a specific operation, and data flows through these stages like an assembly line. In pipeline parallelism, different stages operate at the same time. While stage 1 processes item B, stage 2 can process item A, and stage 3 can process item A's next step. This improves throughput because multiple items are being processed concurrently. A practical example of pipeline decomposition is image processing. An image can pass through multiple stages, such as loading, filtering, edge detection. Each stage works independently on different images or frames, creating an efficient processing flow. This is widely used in video processing, compilers, and CPU instruction pipelines. Let us learn it through coding. I am going to be discussing a program simulating three-stage pipeline: producer, processor, and consumer. So first I will be needing a container. In this case, let me use Q, and let me create a global Q objects for integer type Q1 and Q2. So Q1 will have data created by producer, and processor will process that data and copy it to the Q2, and consumer will consume the data from Q2. So that is what's going to be there. So that data will be stored in will flow through these queues. Q1 will hold the beginning data, raw data, Q2 holds, and we're going to have a tax, producer tax first. This tax will generate the numbers. In the range, numbers 1, 2, 3, 4, 5. It will actually, when I say generate, it will just copy these numbers into this queue, put into the queue. So for int I equals to 1, I less than 5, less than equal to 5, I plus plus, and you have q1 dot push I into it. So this is a very simple producer, just for the sake of simulation, not to complicate the things. And processor, it will actually square the elements from Q1 and copy that into Q2. So while not Q1, while Q1 is not empty, as long as there are elements, you create a X Q1 dot copy the element and remove that element, then Q2 dot push X times X. This is the processor, and then we're going to have very simple consumer. So the consumer will only look into Q2 and then just display it. The way of consuming is just to display the data here in this particular case. So Q2 and prints while not Q2 dot empty, and we want to remove that element from the queue. These are the three, so this is these are stages for producer, processor, and consumer, and then they will be running kind of in parallel. Dealing with these elements 1, 2, 3, 4, 5, and so on. So we have a thread to execute producer, and we have another thread, and then we do join it, and T2 processor T2 dot join, and then so in this case we are running this one by one. First, the producer does its everything is produced, and then after that process, everything is processed and everything is consumed. This kind of sequential all these generation of these elements is carried out in one shot, in sequence, and then producer, and then processing is done, and then after that consumer is actually executed. So in this case each stage performs a part of the computation and passes output forward. Even though the threads are used, it is not a truly parallel execution, because you execute a thread and then you join it back, right? So then only after that this thread goes into execution. But now next I'm going to be demonstrating um, um, true pipeline decomposition based on this code. So the example generates the numbers, computes their squares, and then displays the result. And you know, um, so I need to do some changes to it to make it. Um, I mean, run in parallel, so something like this, right? So, for example, if number one is generated, for example, we want to implement like this. Number one is generated, and then it I mean producer generates, and processor processes, and then consumer does these things in parallel. And then immediately once it is generated, and then after that two may be generated afterwards, and then after that producer, I mean these three things operate on this. So and then you may be have another number generated. So I mean this I mean processor execution doesn't have to wait the completion of the producer. Once data is available, processor can start working on it. That is the pipeline implementation. For that we want to do uh, we want to I mean we need to also have some kind of define the critical section of the code, and use lock to I mean prevent other threads from accessing, because if multiple threads are I mean running this, then there could be possibility of rest condition, data rest issues. So we want to change this producer. um, we want to include we need mutex library, so maybe include mutex here. And we also may need condition variable, and then we also need to create a mutex object. So we will need two objects for transition from producer to processor and from processor to consumer. So condition variable cb1 and cb2. Then with that we want to put this in scope, and so we want to um, have a lock protected. So let me have a unique lock std. And then after that it's going to be, it should be std mutex. And then now we want to print message just to see that it has been produced. And we want to we unlock this the writing and reading writing actually happens in the lock protection, and we want to notify. It will actually notify the next one. So for example, it is notify cb1. So it will come to that in a moment, because we'll see that it is for communicating with the processor. After that, after producer, we're communicating with the processor. So when the production is in the process, we want to notify one, and then if it is done, and then we want to notify everyone. So after that, after the completion, we do locking, and then this is the variable that indicates that it is completed. Done is true, so probably we have not created this variable. So let me create a variable. And then we have done equals to true. Then we have cb1 dot notify all. And so what it will do is it will create and then notify the processor. Processor will pick that value and notify, but it will continue this task will continue running on the thread until it finishes. And for the processor, we want to have an infinite loop here, and that will be a little bit safer approach. True. And then we want to do lock. At this point, we want to set this processor waiting, right? So unless until this CB1 notifies it, this has to keep waiting. It cannot continue. So once producer has completed, it will notify, and then through this same condition variable object, we want to keep this waiting. CB1, call this function, and then you need to send this lock variable. This is syntax you used to use it. All done. So this will cause it to be waiting, and if it is not ready, in case if it is not ready, then it will just unlock it and then go to sleeping again. So if q1 dot empty, if q1 is empty, then it is done, and done. Then just you need to have a way of break the infinite loop. mpty expected semicolon. Yeah, I think semicolon missing here. And we have this value taken out from q1 and taken out, and then we don't we want to unlock it. Then after that we want to compute the result. Let's say int equals to x times x, and and we want to write that data into Q2 now. Once we compute, we write, and in the critical region, so we want to lock again, call this log2 and mtx2, then std, and then Q2 push. So I think we have this thing here, so we can use this command, and we push the result and display the message. Then we unlock, and then we notify one. So CB2, this CB1 will notify, and because we're using CB1 to wait here, so it will notify this processor. Then we use a CB2 to notify, and that will be used for this consumer to be in waiting state. So CB2 dot notify one. This is the processor, and we want to a consumer. Again, we want to have an infinite loop, true, and we want to again lock mutex. Then we want to have this similar to this CB1 wait. We want to set it for waiting here. It's going to be CB2 wait, and it is lock return Q2 empty. It is accessing Q2, so done. Then after that, if Q2 dot empty and done, break. So consumed Q2 pop. So this is the consumer task. Now we can run this together, and we can join it because we are actually getting into the parallel execution. So put it here. Then after that we can display the message saying that pipeline finished. So let me take a quick look into it again. We have two queues, producer push I is created through this iteration, and the push and displayed, and then unlock and notify one, then lock just to write things in this, right? Notify all. We didn't need to unlock here in this case because anyway this is going to go out of scope at this point. And processor lock 1, unlock front pop. So let me try it in the terminal and see what happens. So in the terminal, so we have this terminal, compile, so now in the output you can see it is produced, first it produced and second produced and then processed. It is not waiting for all to be produced. processing is started in the beginning and processed 1, right, and then processed 4, 9, 16, and consumed, and then processing again continues. So they are actually running in pipeline. Production, processing, and consuming are actually running, but they are running. I mean, once the production runs for 1, and when it is done, then processing is ready to use 1, regardless of whether production is working with 2, 3, 4, or 5, right? So that is how the pipelining actually takes place. This program implements a simple 3-stage pipeline using threads. The pipeline is divided into 3 stages: producer, processor, and consumer. The producer generates integer values from 1 to 5 and stores them in the first queue, Q1. The processor takes values from Q1, performs a computation in this case squaring its number, and stores the result in a second queue, Q2. Finally, the consumer reads the values from Q2 and prints them as output. Different data elements can exist in different pipeline stages at the same time, enabling parallelism across elements. At the same time, each individual element moves through the stages sequentially. This design demonstrates how data flows through a pipeline where each stage performs a specific operation and passes its results to the next stage. Even though threads are used, synchronization ensures that data is transferred safely between stages without rest conditions. This model is commonly used in real-world systems such as image processing, streaming pipelines, and compiler design. Now we move from decomposition to program structure patterns. First is the master-worker model. The master-worker model is a parallel decomposition pattern where one central master process distributes work to multiple worker threads or processes. The master is responsible for dividing the problem into smaller tasks and assigning them to workers. The workers perform computations independently and return results. The master maintains a set of tasks that need to be completed. It distributes these tasks to available workers either by assigning them directly or through a shared task queue. Each worker processes its assigned tasks independently, enabling parallel execution. The master worker model improves performance by enabling parallel execution of independent tasks. Workers operate concurrently, reducing overall execution time. This model is commonly used in parallel computing, web servers, map-reduced systems, and scientific simulations. The master may also collect and combine results after processing is complete. Let us demonstrate it in coding. Here I will demonstrate master and worker working together. Master generates tasks and worker processes the tasks. So I will need to create a master worker. Before that, let me complete this library inclusion. I'm going to be needing a vector and kernel. So we want to have tags. Master will generate the tags and it will put in a queue, and the worker will actually pick the tags from the queue. So we use queue integer type, call it tags, and we also will be needing mutex. Now we want to create a master, and the purpose is to generate tags. So master will receive the argument indicating the number of tags to be uh, generated for int I equals to 1, I less than equals to. If the integer values are they represent the tags, then we can start from 1 and we can go up to less than or equal to number of tags, and we're going to have dot push I, and so master assigned the tags. But before that, we want to write this in lock protected mode. So we want to have lock guard text is mtx, and then before that, sometimes we want to do some simulation of some amount of time taking for the masters to create the tags. So it I mean, when master is working to create the tags, it's possible that it may require some time, right? So to simulate that, we want to set this thread to sleep for some time, for milliseconds. So they call this real workload. This thread just let it sleep for 100 milliseconds. Then we want to have worker. The purpose is to process the tasks. So task is I mean, identified by the integer, so this is ID. So worker receiving a number means that it is actually processing that number, and then again in the infinite loop, what we want to do is we want to take the tags from the queue and just display it. I think that's the way we process it. So maybe create an integer tags, and then tags equals to from the tags queue take out and then remove it, then so here we display this message. That means the worker, okay, so the ID carries the worker ID. We're going to be passing that worker ID when we call that function in the thread, so that worker ID is processing that particular task. So we will be able to know which worker is processing which tasks through by displaying this information. But when we write this, we want to write this in protected in the critical section. So lock guard mutex lock mtx, and if there's no tags, then we don't want to continue processing it, return it, tags pop. Now after that, we also want to do the simulation that like in this case we have this kind of real workload simulation, we also want to assume that processing tasks also takes, because we have just here the way of processing is just displaying the data, right? So in real life that doesn't happen like that. So it takes some time to process the task. So just simulate that processing time. So assumption is that uh, producing tasks actually takes 100 millisecond, and but consuming or processing takes 200 milliseconds. So with this master and worker, and there can be multiple number of, typically there could be one master in our simulation, but there could be possibility there could be multiple master, but typically when you're working with master and worker, then it's going to be one master and multiple more than one workers. So we create a master thread, and the number we want to pass argument is number of tasks. So we assume that we have total number 10 tasks, and there's going to be more than one threads, I mean workers. Therefore we want to put those in vector of threads. Then we want to create a worker one by one for, say, int I equals to 0. We're going to have 3 workers, so I less than 3 and I plus plus, and workers and plus back. Then we do join the threads back, and then for the workers, then finally we can display all tags. So this actually shows the real master worker structure. So master works on the task queue, creates the tasks, and then workers actually get the tasks, and we get the output. So they will work together in parallel. So let me first see this output in the terminal. So masters assign the tasks, and then all tasks completed, right? So going back to the code, this was actually displayed, but we are not able to see this thing. So we should be seeing this. We have worker while true, and push back. Let me try one more time. So here we can start with one worker. Let's commit this out, and we use worker thread, then worker 2, and one thing here, we have 200. It takes more time, right? So maybe let me try with this. And see we're working. Maybe reduce this to 50. Probably I think here what is happening, we're setting this master slave in the beginning, and the thread is trying to access in the beginning, and it is just probably it is seeing this task as empty, and it is exiting immediately. So maybe what we can do is move this slave mode to the beginning, somewhere here, and master will slave one it and produce the task, and thread worker will have an opportunity to take the task. So we're going to have one worker in this case. Maybe switch to the previous code. So probably in this case we may be able to see the worker, this message. Yeah, go back to the terminal. Yeah, now we can see some output. So master continued assigning tasks, and worker actually worker 2 was worker 0 2, they were actually processing the tasks. This was because we have not put this C out in the protected in the mutex protection, so it's not in a muted position, so they are appearing like it is kind of random. But if we want them to be ordered, maybe you can put this further in the mutex protection. Something like this. So you can see worker 2 um, process task 1, and then worker 1 process task 2, worker 0 process task 3, and worker 2 process task 4, 0 task 5, task 6, and then so you can see the this master worker parallel design, parallel implementation in action here. So the master generates the tasks and places them in the shared queue, while multiple workers threads independently fetch and process tasks in parallel. This model is widely used in thread pools and distributed systems for efficient parallel task execution and resource management. Now let's look at a very important real-world model, MapReduce. MapReduce is a parallel programming model used for processing large datasets. It consists of two main stages, map and reduce. In the map stage, input data is processed in parallel to generate intermediate key value pairs. After the map stage, intermediate key value pairs are grouped by key. The reduce stage processes each group and aggregates the results. This stage produces the final output. The complete map reduce process consists of 4 steps: input, map, shuffle, and reduce. Map tasks run in parallel across data partitions. The shuffle phase groups data by key. Finally, the reduce phase aggregates results to produce the final output. MapReduce is widely used in big data systems like search engines, log processing, and distributed analytics. To repeat, MapReduce enables scalable processing of large datasets by combining parallel mapping with distributed aggregation. Let us understand it better through coding. As discussed earlier, the goal of this example is to demonstrate the MapReduce programming. Model, MapReduce programming model using a simple C++ implementation. The workflow is divided into 3 stages. One is map stage, map phase. Input data is processed in parallel and each thread generates intermediate key value pairs in this phase. And we have a shuffle, and here intermediate pairs are grouped by the key. And finally we have reduce phase, where the values belonging to the same key are actually aggregated to produce the final output. And in many real MapReduce systems, the shuffle state is integrated with the reduce state, reduce phase. However, in this example, the phases are implemented separately to make the workflow easier to understand. So let me start doing it. First, I need to get have a data here. I want to have a group of collection of or a container of words. Cat, and we have dog, we have again cat, bird, dog. So this is the data we have, and to use vector we need to include the library, vector library. Then we are also going to be using we need to also prepend the name of the namespace here, and um, we will be using a vector pair type. So pair of string and integer, and the object, let's call the object mapped data. This is a global data which is going to be shared by the threads, and we also will be needing mutex. So, and for mutex, let me include library. Now we want to complete a map phase. Map phase will access this global data, and it will actually it will use the global data and then do the mapping of the global data. So let's start with the coding. We didn't need this function to return anything in this case. Map task. We want to make it general enough so that we can apply this in multi-threading. So we want to process from starting from one particular index of the words, start and up to another index END. So we want to start with the local storage, then we will actually copy that local into the global buffer, right? So this is the global buffer. So we're going to having a vector local storage and pair string integer, and so this is the temporary intermediate key value pair storage, and we want to generate the word value pair for int I equals to start, I less than int I plus plus. Then we insert push. This is the pair of words with index I, and we want to just push 1. This will actually generate the pair of let's say the content of the word, for example cat 1, dog 1, something like that. So this kind of pairs it. And next step we do here is we want to copy this local data content into this map data. So for that we want to use the STL algorithm, and it needs you to specify the range from where you want to copy. We want to start copying from local.begin, and we want to copy up to the end, and then where you want to copy. I want to copy to this buffer, so mapped, but it is empty container, so you need to actually either you create a space, or or you can use a tool that actually inserts automatically. So back inserter, so it will keep inserting and increasing the size of the container, and we do this after the we want to protect this because this shared variable, we want to protect access to the shared variable. So create log guard, right? So this region starting from this point to this end of the scope, this is going to be the protected or critical region. Now we want to complete shuffle function. Shuffle function will actually um, do the grouping and return the grouped map, right? So it will we want to have map string and it will actually, what it will do is it has the first element, right? So it will map the name of the word into the total number of count of that word. Right, so but I think to use it we need to include the library map on the top. So and then we need to return this thing, the same type. I mean, this object is going to be returned from this function, so return type is the same here. So and then ultimately once you create group, you will be returning it. And the way we do shuffle is that we access all the elements and we do and this will give access to the word. The first is the word, second is the number 1. So you will be pushing that number. I mean, the numbers are 1, right? So this will actually push 1 value, so you will be pushing once in the vector. I mean, we have a mapping of this word vector, so in the vector you will be pushing 1 1 1 1 into it. So push back, so this is the shuffle phase. And then finally we want to have a reduce tags with the parameter of type map by reference. Just display a message and then we want to aggregate. So the way we aggregate is I mean, do the summation of that item. So it will actually just get you know, so it will actually get the item of this type, I mean something written by shuffle into it, and it will actually compute the summation of the number of ones inserted here and display it. So pretty simple for P initial sum value for int I equals in P dot second. This is a vector, and value. Then after that you and it's displaying word and number of count of the word pair, right? So this is the word, and this will be the total number of values, total number of words, count of the words. So this is these are the tags. We have map, shuffle, and reduce, and in the main function we already have a data in the global space words. So we want to create keep words size, and then we also want to, because we want to run in multiple threads. For example, this first half in one thread, second half in another thread, so therefore we also need to have a middle value and divide by 2, and mapping phase in parallel. So we are using threads. In this case, we are splitting input data and process it in parallel. I may not have included a thread here. I need to include a thread. And T1, we want to map from 0 to mid, and then join back to the main thread to T2 join. Then after that we want to do shuffle. So there's a correction here. And shuffle data will return something. So it will return this type. So you can use this type, but many times it is convenient to let the compiler infer it by using keyboard auto. So group data is equal to and then and you pass that into it. So I think this is all we have. So this is a very basic program that actually demonstrates at the very basic level the map reduce. Map reduce is one of the technique that is widely used. So this is a code that actually it tries to help people understand what is map reduce. So it again, just to emphasize it, it processes the input data in parallel, and it generates the key value pairs after that. Then the shuffle groups the value by key, and the reduce aggregates the final results. And this model is widely used, as I told you earlier, in big data platforms and distributed computing systems. And in the end, let me make sure that we have our code is working. So I'm compiling it. So you can see the count of the bird, cat, and dog is determined. So if you compare with the data, let's see. So bird is only 1. We have 3 cats, and we have 2 dogs. Next is fork join. This is closely related to recursive parallelism. The fork join model is a parallel decomposition pattern where a main task is divided into smaller subtasks that execute concurrently. The fork step creates a parallel tasks or threads. After all subtasks are complete, the join step synchronizes them and combines execution back into a single flow. Execution begins with a single main thread. During the fork phase, the program creates multiple parallel threads to process independent subtasks. The join phase waits until all threads complete before continuing execution. This synchronization ensures that all parallel work is finished before the next stage begins. The fork join model follows a divide and conquer strategy. Large problems are divided into smaller independent subtasks that execute in parallel. After processing, results are combined during the join phase. This model is commonly used in parallel algorithms, recursive computations, sorting algorithms, and multi-core processing frameworks. Let me show this in a coding. Here I will be demonstrating fork join using recursive and divide and conquer approach. You may find it similar to what we did in divide and conquer method in the coding exercise, but as I told you earlier, this fork join uses this strategy. So let's get started. I'm going to be needing data containing 1, 2, 3, 4, 5, 6, 7, 8, and we want to have a function which runs in recursive way, and so it's going to be having base case and the recursive steps. In the base case, this is a exit condition case. So in this case, if this the difference between this start and end is less than or equal to 2, then you do this computation. If in minus you don't want to go further into the recursion, int sum equals to 0, and then for int I equals to start I less than end I plus plus, then sum plus equals to data I return sum. This is the base case, and then after that you need to find the middle value, and mid equals to plus int divided by 2, and int left sum equals to 0. You want to take summation on the left side, int equals to 0, and now you do the fork. So doing fork is essentially recursive invocation of this function, but we're doing in thread in parallel T1, and we're going to have another thread T2, capture parameter the body. So in parameter we don't need anything, and we will need to use left sum here. Let me change this to uppercase S. Left sum equals to so now this is not accessible, so you need to access, but you want to access by resource reference, because you want to write the data into it, and start mid also not access, so maybe we want to access, capture start and mid. You don't need to you don't need to capture this by reference, because you're just using it, you're not making any change to it. In the second thread, we want to capture write sum and start and end. Then write sum equals to mid to end. Mid and end capture and use it. So this is the fork, and then once you are using thread, then you need to join it. Then finally you want to combine. So this is the function that will implement this entire thing, fork and join. And in the main function, we want to have some data, some code to use it. We only have data, I guess. This data we're going to be using in the main function. And that is global, so that is accessible directly. So maybe we want to send the starting and ending value in the beginning in the overall case, which is sum first 0 and data size, and it will return the summation. So int total equals to this one, and then you so I think we have this s lowercase. So I think that should be it. So it will divide, fork and then join, fork join. That is a process, and each fork will actually compute the value, and then it will combine those values. So let me make sure that we don't have any problem with this code by compiling and executing it. So total 36. I hope it is correct. Let me go back to the code. We got it's 8 9 7 8 9 9 9 6 4 3 9. There are 4 nines, right? 9 times 4 is equal to 9 times 4 36. I think that's correct output. But this is the one very simple demonstration example to demonstrate fork join implementation. Right, so just to repeat it again, the tags are forked. This is a task, summation computation task. They are forked, and they are executed in parallel, and then they are joined. And this actually improves the performance by allowing independent tasks to execute concurrently while maintaining the synchronization through the join operation. Fork join commonly implements divide and conquer algorithms in parallel. Divide and conquer defines how the problem is broken apart, while fork join defines how the subtasks execute concurrently and synchronize. The fork join model is a fundamental concept behind many modern parallel frameworks, including OpenMP tasking frameworks. Now, the final question is, how do we choose the right parallel pattern for a problem? Different problems naturally fit different parallel decomposition strategies. For example, merge sort fits divide and conquer, image processing fits data decomposition, web servers often use a master worker, and word count is a classic map reduce problem. Each of these patterns represent a reusable way of structuring parallel programs. Instead of designing parallelism from scratch every time we map the problem to a known pattern. This helps simplify design and improves correctness and performance. So the key takeaway is simple. We do not randomly write parallel code. Instead, we choose a parallel pattern that matches the structure of the problem we are solving. To summarize today's lecture, we started with sequential versus parallel thinking. Then we learned PCAM methodology. Then explored decomposition patterns. Then studied program structure patterns. And finally, how to match patterns to problems. Once you understand this, frameworks like MPI, OpenMP, and CUDA become much easier because they are just implementations of these ideas.